Thank you for joining us. I'm Brian DeLuca along with Nicoletta Mino, and we'll be your host today for this live chat, Mastering Analog and Mixed Signal Design with QSpice, sponsored by Mouser Electronics and Qorvo. We have a great panelist, and this is a live chat, so make sure to ask your questions in the Q&A at the bottom of your screen. And now to Nicolette.
Good morning or afternoon. Today we are here to talk about Qorvo's QSpice for analog and mixed signal simulation, which gives power designers the ability to evaluate their designs with complete confidence. And who better to chat with than the creator himself? Mike Engelhardt joins us to tell the story behind QSpice, provide some tips, and answer your questions live. So make sure you ask them. Thank you so much for joining us, Mike. We do appreciate you being here.
Happy to be here.
All right, so why don't we dive in, and we'll keep it easy to start off. Why don't we kick off with the background story? So, SPICE has been around for a long time. Why write another SPICE program?
Well, the deal is Berkeley SPICE is a difficult code. Even if you've had someone from the original Berkeley CAD group explain it all to you, and even explain why it was written the way it was, which is rather intractable, even if you have the benefit of that experience, it's still a difficult code. And it's normal for something that's that complicated to have room for improvement. And frankly, since numerical methods and computer hardware have advanced so much over the 50 years that SPICE has been around, there was a lot of room for improvement. But ultimately, I wrote QSpice because simulation requirements changed. I mean, I'd love to be able to do just pure analog. Analog electronics is fascinating. It's a beautiful combination of physics, math, and cleverness. But today, everything uses at least some digital. It really isn't possible or even desirable to do pure analog anymore. Even power conversion benefits greatly by applying digital methods. And more broadly speaking, ultimately, every interesting result is converted and communicated in digital. We don't live in an analog world. We live in a digital world.
Mm-hmm.
So front and center to QSpice is that is the mixed mode simulator that handles current analog simulation requirements. QSpice allows massive amounts of digital logic to be presented to your SPICE simulation.
So there are many SPICE programs out there. Some of them are free. Why would a person, use QSpice?
First, because it's a better SPICE program. It's better at SPICE basics. That means that if you just give QSpice some traditional SPICE style transistor level circuit, QSpice will be better at finding the solution. And for many people, that alone is compelling. Also, you have the ability to present arbitrary large amounts of digital logic to your SPICE simulation. QSpice includes optimizing Verilog and C++ compilers that reduce your own source code to native Intel opcodes that are executed during the simulation. The result is that the digital part of your simulation typically evaluates faster in QSpice than the hardware itself can. QSpice leverages the benefits of modern computer hardware. QSpice uses the GPU shaders to draw lines very fast, about 100,000 times faster than a CPU. Plus, the CAD drawing and waveform data are better rendered with the GPU than a CPU can. You're looking at desktop publishing quality graphics all the time. And actually, I have to say I enjoy the irony that the fastest computing hardware for scientific and engineering computation is built for teenagers' computer gaming needs.
It's funny. It's funny. I was going to ask that because you see a lot of things now being processed in a GPU versus CPU because of the power behind them.
Well, GPUs are good for some types of computations, but not other type of computations. There are SPICE does not advance very much with the GPU. Wow. There are some claims that you get, maybe a 40% increase here and there, but those are highly selected test cases. The problem with SPICE is that it's very hard to run a lot of stuff in parallel, and you need a lot of internal accuracy, which a GPU doesn't have. CPUs, for bizarre historical reasons, have more than 64-bit internal precision that you can, some compilers can access this extended precision, and I use that. But anyway, the irony is great, that the best scientific and engineering computers were for gaming. Teenagers need faster computers so they can score more points in their video games, so they can buy more weapons, so they can kill more zombies from outer space. It's all good. It's all in the name of progress.
Right. It's true. It's true. Well, that's, it's probably where like a bulk of the money is being spent, right? That's why they're focused, some of these, computer companies and these companies that are making these, they're focused on the gaming because that's probably the bulk of where the money is, right?
Well,
Absolutely.
what's the alternative? Where would you prefer to see all of this great engineering minds go?
I'm not the person to ask. I actually have never played a video game in my life. Okay.
Stop.
Not even Tetris. Come on.
No, I just haven't played any of those games. But I build computers that are like, ultimate gaming rigs, and I read the gaming hardware review stuff and try to separate where's the actual performance and versus just a bigger heat sink so it looks cool, but
right.
Anyway.
That is ironic, Mike.
Yeah.
All right. Can I call out the elephant in the room for one moment? Because, we've scoured forums, we've talked to plenty of people, and we see that some users seem to be wary of QSpice. And I'd love to know what your response to that is.
Well, I understand. QSpice is new. It takes time for people to realize that something as huge as QSpice is for real and for free. And looking back at my own prior work in a previous life, I remember people didn't want to drop PSpice and move on. They had invested a great deal of time learning how to use PSpice, and some had become the resident expert in PSpice at that company. That was their very livelihood, was their ability to run PSpice and work around its limitations. So when a new simulator came along that I had written, and that new simulator outperformed PSpice, well, you can imagine the horror. The resident Spice expert had been using the wrong spice. The cognitive dissonance kept people on PSpice way past its expiration date.
Right.
So it took me a few years to knock PSpice off the table, but I did. And now I will again knock off every spice. I will knock every spice off the table and leave only QSpice. And it's inevitable.
I like that. I like that goal. I like that goal. Now, so what do you think it's just because people are weary, really just because it's the new thing and they're so used to using whatever there, right? What's in front of them versus going, hey, let me just go download this new one, see how this works.
I think it's because it's new and they don't yet understand that how transformational QSpice is. That it is. It's not a QSpice started out as a mission to just get Spice right. I've been working on Spice internal since the mid 1980s, and I've written a lot of Spice programs, and I've written even more simulators. But when starting 3 years ago, I thought, Spice is just so complicated, and there's so many things I did in prior refactoring of the code that I just wanted to get Spice right once in my life, and that's how QSpice started. Right. But then I started getting involved with Qorvo, and it became much more than that. It became this wicked powerful mixed mode simulator. It will actually evaluate digital faster than most hardware can. Unless you put a Pentium CPU in your analog circuit, and then it would just run at the same speed. But usually simulations run much slower than the hardware, but QSpice breaks that for the digital aspect of it.
I do see someone here is telling us why they're not using QSpice. So for example, their work will not allow them to load QSpice onto their networks.
Well, that's not a technical problem.
Right.
And that sort of problem also existed in other simulators that I've written earlier. Um, there's nothing that I can type on my computer here and fix that problem. It's something that he has to fix at his infrastructure.
Right. Yeah.
Right.
It's a business decision, right?
Yeah. We do have another question here. What is the scope of QSpice and mixed signal IC design, especially the analog and digital circuits with CMOS and SPICE levels, as in the submicron levels?
Okay, there's one thing I should mention about QSpice is that in the first year of its development, it was actually written for ASIC design. And so the idea was you would QSpice would be the front end to a custom ASIC house. You would the idea was that you wouldn't need an IC designer to design an ASIC. You'd give someone the simulator, which at that time I called SPQR, just as an internal code name, because you can't trademark. It's like, ancient Rome, you can't trademark SPQR. So SPQR included blocks of IP that were implemented in deep submicron or nanometer structure, and these blocks from the pins out would look like they were implemented with transistors, but inside they were digital, they were logic. So they behaved exactly right, deep submicron devices, but it would just run blindingly fast. That's was the original version of mixed mode simulation in QSpice. And now moving on from that to bypass this and just run source code itself, that takes the speed and capability way beyond that. But if you're actually worried that there's something special about deep submicron stuff, then you should just run the BSIM4 models, which are supported in QSpice. You can just run your IC netlist in it. So I think we have that very well covered.
Right. So there is another question here from a user, and so basically what they're asking is, because this is free, is it tied to some proprietary I can get that out for a second, libraries?
Okay, so this is actually I really appreciate this question because it's extremely important. And I meant to get to this and why you'd use QSpice over something else. The thing about QSpice is that it's universally available. Okay, everyone can download QSpice, even competitors, and they're free to download it and use it as they wish. And they can even author simulation models of their products and distribute those models as publicly as they want, even if those models compete with QSpice, even if they compete with Qorvo. That's unique. It is actually truly universally available. It's actually free, and it's surprising. I wouldn't expect someone to expect that from QSpice, but it is a surprising reality. But it's just Qorvo doing that is they've made QSpice their contribution to the electronics community to introduce themselves as a broad market power electronics supplier. So yes, you should drop other spices. You should move to QSpice, and in particular, all the IC manufacturers should do that because it's universally available. Everyone can get it, and the modeling language of QSpice is so far ahead of anything I've written before that it's much easier to model stuff in QSpice. I mean, I have personally modeled many hundreds of switch mode power supply controllers, very many hundreds. And from that experience, I've thought of a new modeling language that I use that's in QSpice, well documented. You can all use it, and the effect is that one individual can replace a large group of modeling engineers if those modeling engineers are hampered with prior versions of Spice, even if they were written by me. That's a really big deal. So other companies are welcome to standardize on QSpice, and they should for their own financial reasons.
So you did mention power in there. So What special support of power electronics does QSpice offer?
Well, quite a few aspects to it. Um, in a nutshell, QSpice is current with the advances in power,
Mhm.
with current power design. There's new types of transistors. See, power transistors are normally difficult to simulate in generic SPICE programs because SPICE was never about power transistors. SPICE was about IC design. The letters IC in SPICE stand for integrated circuit. And since you can't print a power transistor on an integrated circuit, there was no support for simulation power transistors. So in QSpice, I've extended the device equations to handle current power devices, vertical MOSFET, GaN,
Mhm.
silicon carbide. Those are all native device types. And you have to extend the device equations quite a lot, not just match the saturation region and the infinitesimal current triode region and infinitesimal current, but there's extended device equations that have a physics-based transition between triode and saturation, quasi-saturation, even for FETs. So it's a major advancement in handling these devices, and also GaN doesn't have a body diode, so it's hard to turn off the body diode or substrate diode in a normal splice. So when a GaN is in, if you make a bridge with GaN, it will look like it has body diodes because it will get conduction even if the thing's not turned on. But that's just the channel inverted, and it's turning on the threshold voltage instead of a diode drop. So it has all that behavior in it. It has the gate leakage of a GaN. It has the charge model for these other devices. And it even has um, a level 2010 MOSFET, which is a native circuit element that handles Qorvo's Cascode FET design, which is two dice bonded together. And it has the two dice with all of the inductances from the internal bond wires and including one device that has this, you can make an equivalent circuit with a substantially reduced number of nodes. So that's one thing, is that you can simulate the power transistors. Another thing is sort of relating to power transistors, that QSpice is the first SPICE that computes dissipation correctly. Okay. It doesn't just, all of the device equations are redone to separate out the dissipative real currents, that actually cause thermal heating, and the usually what's a displacement current, a current that goes into a capacitor, which is a current, and it stores and it stores and releases energy into the rest of the circuit, but they're non-dissipative. So it separates those. When you plot the dissipation in a device in QSpice, it's the actual dissipation that causes thermal heating, and that's not been done before. I mean, most people don't know the device equations well enough to, separate displacement currents from real currents through all the transistors in SPICE. But since I've been dealing with this for so many decades, I can do that and just get that right. And there's other aspects that are desirable for um, uh, power simulation. Having nonlinear reactances. QSpice has nonlinear reactance. It even has arbitrary reactances. We can say, the capacitance is a function of a whole bunch of other stuff, and these can even handle transcapacitance, or the capacitance between these two nodes depends on the voltage on these two nodes. It gets all that right. It conserves charge even if expressed as capacitance and not charge-based, with new methods of integrating differential equations that haven't otherwise ever been put in SPICE. So that's kind of interesting. And but possibly the most important aspect for pragmatic power application design is that you can have massive amounts of digital logic in your simulation, because there's so much digital today in power design. I mean, there are chipsets that program other chips in the set over I squared C to tune the circuit so that the system learns the best operating point. And you can simulate all that. The one thing about QSpice is that you can simulate a literal model of your circuit. I mean, let's just back, engineers take some big complicated circuit, some big complicated system that you can't solve, and then they break that into little pieces that can be solved. That's what engineering is. Okay. But in breaking this big circuit into little circuits, you sometimes have to simplify things so much that it's not a literal representation of that little piece of circuit, and you may have lost the behavior that you need to understand to get the system working. And in QSpice, you don't have to do that. You can simulate the chunks that you simulate in PSpice are fantastically larger than you can do in any other Spice program. So that's really why it's useful for power, those aspects.
So we do have another question. Can QSpice be run from the command window in no graphic mode just to get data and reuse the data?
Yes. So QSpice is different than what I've done before in that it's actually many executables. And when you're running, in the past I used multi-threaded, and in QSpice, yes, it's multi-threaded, but it also uses multiple processes. And this helps with memory filamentation. That is to say that if you allocate a bunch of memory and then free stuff, sometimes the holes don't get used and the process spills out of the cache when it shouldn't have to if the software was implemented differently. So QSpice runs in different processes. So you have, it stays in cache much better. And that's where it gets a lot of its simulation speed. There's that can speed things up literally by an order of magnitude because cache is so much faster than RAM. So the simulation itself are a separate command line application, and you don't have to fire the GUI at all. The names of these programs there's QSpice 64 and QSpice 80. Those are two different simulators. Both QSpice 64 and QSpice 80 use a mix of double precision and extended precision, but QSpice 80 uses a larger mix, computes even more of it in extended precision. So it runs a bit slower, but it's more accurate. So those are the two simulators itself, and the command line arguments for those are well documented in the help. The GUI is called QUX, the Q user experience, QUX.exe. That is that's everything that's all the DirectX graphics,
Okay.
but that is actually invoked many times by one simulation because the waveform window is in a different process than the CAD data. And that's so that when the QUX implements its own 64-bit address space to page in waveform data into RAM, and those all run in their separate processes. So, and then there's QPost, which is a post processor that executes .measure statements or .for statements. That's also a separate process.
So, what would be, and we do have some folks asking questions about a demo. So I just for the audience, we will be showing something in a few minutes. But, Mike, what would you say your advice to someone who's just getting started with QSpice? What would you say to them? What is your advice?
Well, I think it's time for the demo. I mean, the first thing you should do.
Let's get right to it.
Yeah, let's hit it. So let me share my screen here.
All right, and we'll address these questions that are coming in while we're doing
some
the demo
people
as well.
Yeah, and some people actually are asking specific questions to see in the demo.
Yeah. Okay, great. So let's so the first thing you should do is install it. So this is how you get QSpice. If you go to your favorite waveform viewer or your favorite web browser, www.qspice.com.
Mm-hmm.
That's the magic incantation. And it's a vanity URL that directs you directly into the Qorvo site that says where to get QSpice now.
Mm-hmm.
So once you install it, you get an icon on the desktop that looks like this. And the first thing you should do to answer your specific question, how to get started, the very first thing you do in QSpice is run some simulations. Okay. So under File, Open Demo. These are example circuits you can immediately run to get your dip your toe into QSpice. Here is look, here's a simple circuit. This will be a crystal ladder filter, and you could run this simulation and look at the response of that. Let's look at another example. Open. Here is Oh, I pressed save instead of open demo. Let's run this one. This is a switch mode power supply. This would look like a macro model of a switch mode power supply. Let's run. Okay, so here we have it's a buck regulator, and this thing implements frequency fold back. The oscillator is phase locked to an external clock. The switch logic of the PWL is that it is residently switched. The PWL uses a triangular wave based on the current. So this is going to implement a current mode controller. And well, let's run the simulation. Run simulation. And so that is the output. This waveform is the output voltage. You can see it sort of do a soft start over a millisecond and come into regulation. I made it a little ANSI so you can see it ring into regulation. Looks a little bit more interesting. This is the voltage on the output of the phase frequency detector, and you can see it acquire phase lock. So what's happened here is that I've simulated 5 milliseconds of a 500 kilohertz switcher doing a startup transient analysis and coming into phase lock, and that's simulated in just over a third of a second. QSpice is fast. Okay, there's just no other way of describing it. Okay. Let's look at an example that starts showing what QSpice is really capable of. There's practical switch mode power supply. Okay, this is an example that's very much worth studying. This is this particular part is similar to some you'll find in industry, and I've implemented the model as a hierarchical design, so we can actually look inside the model, right-click, enter schematic, and so oh, I have little cartoons here I don't need. These are some you can put bitmaps on the schematic. Okay, so this is the macro model. All this stuff is combinational logic. And these are, again, with ASIC model equality and gates and flops. These things all draw power appropriately from the rails. It's easier to make models if you actually have parts that draw power. It has thermal lockout here. But the magic is this part here. Now, this looks like it might be another hierarchical design, but it is not. If I go right-click, C++ interface, open C++ source, we can see the source code to that device. And this is a constant on time. You see, it's a very simple program. It's just a couple of pages of code that implements a constant on time, does time step control. It handshakes with the simulator and how to, what time steps it should take. And it's a deceptively simple algorithm that, though constant on time, is also constant frequency. And it has current monitoring so that it doesn't overcurrent. We'll run the simulation, and you can see this thing run 3 milliseconds. It's a 500 kilohertz switcher, and it simulated that 3 milliseconds in just over 1 second. That's, again, an example of it being exceedingly fast. And everything is included in the model. Let's try shorting this thing out. Let's make this a milliohm. You know what? Forget that. Let's just short the output. I'm pointing at things and pressing the delete key. G gives me a ground. I'm just going to short the output and rerun the simulation. I'll extend the simulation time, and you can see it's experiencing a fault here. And what is happening is that's the inductor current. So if we look at the inductor current, it tries to do some cycles, and then it hits up to too much peak current. It just decides to turn off. And then it goes through a hiccup cycle of 10 milliseconds. Right, so everything is there. Everything is, all the entire behavior is there. I mean, every single current from every single pin is drawn from the right other pin. And, it's a complete model. And you can see it's a simple circuit. It's a very simple circuit with like 2 pages of C code, and even has this feature that has an LDO, and it switches over between different rails. This is an example it's really worth studying, is this practical switch mode power supply. You can really see, how to write a program in C, which is recommended over Verilog. It'll be faster to do it. Using C is better than using Verilog in the simulator. You can use both, but anyway, that's the idea. So let's, those are the examples you can find. Let's give you a little tour of the GUI. So the thing about QSpice is that it's going to be a lot more modern GUI than you've seen before. Everything is right-click menus. See right-click, and here's all the menus. The keyboard shortcuts, if I press a J, I get a JFET. If I multiple
Right.
depressions of the same key will cycle through different JFET symbols. Same with Q. Here's the different bipolars that you can get. MOSFETs. Press M multiple times, you get different variations, different types of MOSFETs. Or you have the symbol browser over here. You can, if you want, you can drag a symbol from the symbol browser. Of course, you have unlimited undo and redo. Let's now by being a more modern GUI, for one thing, it has almost no dialogues. The problem with the dialogue is that if I right click on this, most Spice programs will jump over to some dialogue, and then you have to edit it, and then your eyes have to jump back to this section. And an old man like me doesn't like his eyes jumping around the screen. I don't know how you young kids feel about it, but I don't like it at all. So everything is edited in place. As you edit, it tries to see what you're editing. And underneath, you'll notice that it has a hint as to what to type. And these angle braces are it's kind of a software cursor that tells you what part you're editing in. And if you get it all in, it gives you the thumbs up that you got it up, right? All right. All right, let's put in a sine wave here. And let me show how to write C in this. So when you right click, draw a hierarchical entry. So we draw a little hierarchical entry here. And I don't want this. Normally, a hierarchical entry means that a symbol is another schematic. And I showed that with the practical switch with power supply. Instead of doing that, I'm going to actually say that this is going to be a C source code thing. And so to do that, I have to change the symbol property from not having a symbol type to being a DLL. Okay. Now this is going to be a DLL. You have different right-click menus. Let's add a port. Let's call this one in. Notice that when this is in place editor, I can change the justification. If you click on one of these red dots, you change the justification. It'll be there. And I have to say the port type, whether it's an import or an output, that'll be the input. And you have to say the data type. All these different data types are supported. Let's make it floating point. Honestly, floating point is what I use most of the time. All right, let's Control C, Control V, Control E mirrors. Let's make this out. And I change the data type, the port type to output. Great. Let's hook up the test vector to this thing. Now let's type in some C code. Right click, C++ interface, open C++ source. It says, what are you talking about? You don't have any C source for this. Should I make you a template? Yeah. And let's just do the simplest thing first. So what you're looking for is a function name, and you just write how that function is evaluated. These are the pins, and it gives you variable names that will be these pin voltages. And let's just say out is equal to in times in, and that'll be, so it's going to square it. Now here is the coffee grinder next to compile DLL. The coffee grinder is the international symbol for compiling. Okay, and you see it compiled. Let's run this. Oh, I have to give it a tran. And you notice it's giving me that hint on the bottom as to how to type the syntax in. Let's run the simulation. And here we have the input, and there we have the output. That's how easy it is to enter, write stuff in C. Okay. Was that good for you?
Yes, we do have a
We have a
bunch of
couple of
questions.
Questions,
So,
yeah, about the software.
I was going to do Verilog. You want to see? You want to do
Right.
questions? You want to do Verilog?
Let's see Verilog first, and then.
All right. Well, that's great. I was hoping you'd never ask. Let's do Verilog. Okay, so I point at this, Control C, Control V. I'll give it the same vector. This name is going to be the name of the DLL. I have to give it a different name. So now the data types are all good. Right click, Verilog interface, open Verilog source, same thing. It doesn't exist. Should I make you a template? Yeah. So here we have a pin, a block with an input and an output, and you have then a Verilog module input and output, and you say what you want it to do. Let's just do the simplest thing. Assign out equals in times in times in. Compile the Verilog. Again, the coffee grinder symbol. It verilated. It made the DLL. So now we have the input. That was the C++ code, and this is the Verilog code cubed. So, I mean, you just draw a symbol, type in some code, and it will compile and run it for you. I've put some thought into making it as easy as possible. And I would encourage people to learn how to write these things in C++. That's the way to go. If you have a lot of logic, and I've done parts where the part's very complicated. It has I2C, and it has hundreds and hundreds of different internal registers and lookup tables to tend on parameters that pass through it to say how the part was programmed from the factory, how the ROM was burned at the factory. And it runs, and it's 100 pages of C code, and it does not slow down the SPICE simulation at all. It's a big deal. And the practical switchboard power supply example will really show you the use of it. I can show how to include you want to do some questions? You want to import some third-party models first? What you want to do?
Well, actually, there's sort of a question on third-party models. In terms of libraries available, where QSpice stands on reusing the available PSpice models from different IC manufacturers. I guess
Okay,
is that
great.
sort of the same question?
Sure. Let's so I do have a model here that I just downloaded from TI site. I went to TI site and I looked for what are they promoting for an LDO. So this is what that LDO model looks like. All right. This is the file from them. Great. So to import this thing, you just take the thing, drag and drop it into QSpice, and it says, oh, I think you were trying to drop in a model. For the TI parts, you usually have to check this file, include entire file, because being PSpice, they don't have hierarchical subcircuits. Everything is, if you have a subcircuit that calls a subcircuit, it's loose from the top one, and you have to say include the whole file, because maybe the top one includes all those. So there we are. You just say yes. And okay, we'll make a symbol. I realize it's ugly. You can rearrange, pins to make it look a little bit better. But or you could put it in the graphical symbol editor and make a symbol that is actually fairly significant, But anyway, let's hook up this part. This is ground. Let's connect it to ground. I'm going to make a 3.3 volt regulated supply. I'm going to give it 4 volts. So it has a little headroom. I'm going to enable the LDO during the simulation. So I'll make this a PWL. It's giving me a hint of what the syntax is. So at 1 millisecond, it's going to be 0 volt, and 1.01 millisecond, it'll be 1 volt. That'll enable it at 1 millisecond. I'm going to need a resist. I'll use the adjustable version of this part. So I'm going to need a voltage divider to program the output voltage. I need a capacitor, this part 1 microfarad. I actually read the data sheet on this. I know I don't read. I read the data sheet. 1 microfarad is plenty for this product.
So can I just make one comment? As you're going through, you're hitting all those shortcut keys to bring in all these, like you're hitting the C and the R, correct? Like, yeah, because
I just do that. I just type
Yeah.
You know,
Which
it's
is,
it's like
which is
it's like the story of my life. I don't actually do anything for a living, but I type really fast and I'm a wonderful distraction. You know, it's basically
Sorry.
the
Yeah. But I guess my point is this, because even, with all types of software, like once you know shortcut keys, life becomes so easy, right? You're just hitting, your C or your V or your R, whatever the keys are you need here. And it's just,
yeah.
it makes it go so much quicker because I'm
And
just watching how quick you're
you
doing
can
this.
find the all the keyboard shortcuts are in the help file.
Mhm.
If you go under schematic editors, keyboard shortcuts, those are all the keyboard shortcuts.
Right.
Now I'm going to run this at the rated current of an amp. So that's my simulation. Let's run this thing. So there it is. That's how easy it is to run a third-party model, draw a schematic, and see what the thing does. I try to be a little bit practical about it. Say you actually want to buy this part, you can point at it, right click, buy now from Mouser, and it will land to the product page of that part, and you can see how many they have in stock and go from there.
Pretty cool.
I point that out because you guys are from Mouser, so you're like my best friends now, right? Right? I mean, so other CAD features here are I've tried to put a lot of convenient stuff in here. Like say you want to add some source resistance here. That's all fine. It looks the same. But say you decide, oh, I want to stuff that with a jumper. So you could right click, stuff with jumper. Now it's a jumper. I can disable parts. The semicolon key will comment a part out. If I delete this thing, and if it's shorted with a jumper, then it replaces it with the actual wire connection. Parts, uh, let me, it supports 45-degree rotations. So say you want to make a diode ring mixer. That's okay. Hold the shift key, drag the mouse. Now I'm selecting these part, and then Control Alt R will rotate in 45-degree increments and preserve electrical continuity. So you have 40, it just means you don't need a different diode. If you want the schematic to look right with diodes at angles like you would in a diode ring mixer or a full wave rectifier, you don't need to have a diode drawn cockeyed to do it. You can just rotate parts 45 degrees. And one other thing, since I'm on a roll here, say you have QSpice is pretty good on the waveform viewer. Each waveform is in its own process space. So if you're looking at two different simulations, these are different processes. But say you want to look at overlay them, or you can press on this, type Control C, come over here, Control V, and now that was the same. That was not fun. Sign. I want to look at sign 2. Yeah, here we are. So this is a different simulation. I was overlaying something with itself. Control C, Control V, and now you're actually overlaying the two simulations. Now looks a little strange because they both have the same name and they're different colors. What's up with that?
Right.
Well, if you point at the thing down here in the status bar, it will say what simulation it's from. Or in here, you can hold Control L and hide the overlays or not. And you can have an arbitrary amount of overlaid files. Here's a square wave, Control C, Control V. Those are all for different simulations. So that's a lot of, in Spice, you normally don't have to overlay different simulation results. You usually write a .step command, and that's all fine. QSpice will handle .step. And actually, .step is the preferred way of doing it. But people coming from non-Spice tools aren't that comfortable with .step. They just want to overlay data. And so I've added support for that. Also, one thing you want to do in all three models is overlay measured data with the simulated model result. So this is actually a CSV file. You can look at to manage overlays, Control O, you can see what file is there. And that was just a CSV file that I've, from measured data, comma separated values of frequency, amplitude, frequency, amplitude, frequency, amplitude. And you can overlay that and see whether or not your model matches the measured data.
So Mike, we have a question here. QSpice creates trunk function to DLL template. What allows users to control time step dynamically. Let's see, the documentation how to use trunk function seems to be a little minimalistic. Could you explain how to control time step by trunk?
Okay. Yes. So let's put a hierarchical schematic. Oh, I know. Let's look at that's one reason why you'd want to look at Switchwood, practical Switchwood power supply. Right click, enter schematic, right click, open source. So there's two functions. If you're going to implement .trunk, you need to have two different functions implemented ideally. Sometimes you can implement .trunk by itself. And basically, let's start with the .trunk function here. So what you can get to make a template from this that if you just if you check the box when you're generating the C++ template, it will make all of this template. And the only thing it won't do is it won't have these two lines, which is how to tell whether or not the simulation changes. So what this trunk function is doing, it's saying, okay, what are the outputs? And you save the output vector. And then you make a copy of the instance. You say that this instance, so the instance is called structure Acme Semi, and you make a copy of it. And then you evaluate that with the current waveform data. And then you have to write, how do you tell whether or not the states have changed? Now, this is a simple part. There's just a thing called state. If the state has changed, then you say, well, use a time step of whatever the time tolerance is, which is the nanosecond. And I've written that to be a nanosecond. So if anything happens to change the state of the PWL, it says don't take a time step bigger than 1 nanosecond. Basically, it's a temporal tolerance. If you have a mixed mode simulator, people are familiar with voltage tolerances, charge tolerances, current tolerances, relative tolerances. But if you're going to have logic, there's not a tolerance on 0 or 1. Is the tolerance would be when it turns 0 or 1. It's a temporal tolerance instead of a floating point tolerance. And so that's what that temporal tolerance is here. So that's what that does. However, when you add this, all it can do is correct the current state. And sometimes it might take way too big of a step. And so in this particular case, I implemented execute back step size. This simulator, this model is written in a situation where there's always going to be enough time step because there's an inductor current and has to run, local quotation error on the inductor current. So it doesn't need a strategy for how big of a time step it takes. But you probably also want to implement a maximum time step size where just say, no matter what's happening, don't ever take a time step bigger than this. And usually what you would write into this, you would say that if the part is enabled, don't take more than 5 microseconds or whatever would be some fraction of a period. Don't take something bigger than 5 microseconds. Step over a whole switching cycle. But if you're not enabled, take a millisecond. I don't care when you enable. I don't care when you turn it on. It's good enough. So that's what you would normally write there. That's the logic to that.
So we have another question. Can QSpice run under Linux?
No, it doesn't. Again, QSpice is targeted at gaming hardware. All right. And Unix and Linux people could say everything they want to about graphics, but all the graphics party is for gaming hardware. That's where the hardware is. That's where the drivers is. That's what the technology is. That's it's a force bigger than me. I don't even play these gaming hardware. So that's for anything to do with graphics. It's native Windows, and it's using DirectX. And people can say all they want to about everybody's claiming that this is faster than DirectX, and the DirectX people claim that they're faster. But the world is on DirectX. That's where the party is. Mm-hmm. And you show me a Unix system, with 5,000 shaders in it,
Right.
or a Mac with, I love Macs. No one, they're like the holy grail, but you won't find a Mac with 5,000 shaders in it.
That's
So
well, that's also
it's
why a lot of people who game don't use Macs, right? Let's
yeah, I didn't want to bring that up. I wrote a version. I wrote a CAD simulator for a Mac once, so I kind of feel bad that I just poo-pooed on it. My bad. See, if this
So we're
were
not
if this were
poo-pooing,
were this not live, we'd edit that out. Okay, I'm just and let me give some disclosure there.
That's right. We love Macs. We love Macs.
Yeah. Hey, I love Maxie, my little iPhone 15.
Yeah, same
Yeah.
here. Actually, I'm running on a Mac right now. So
All right, Mike, we have another question in case anyone's wondering. I'm not using a Mac. That's what I was. Can Q convert ADS models?
Not particularly. If there's something specific to ADS, then I don't know if I can run it or not. Now, there's going to be a lot of commonality, a lot of device equations, a lot of the transistor equations. QSpice will handle, BSIM 3 and 4, handles the up-to-date versions of each. Well, BSIM 3 is static at this point. But, will also handle, Mextran 504, current version of Mextran 504. It'll handle, many to most of the semiconductors you find in ADS. But if there is some special ADS proprietary feature, odds are I haven't run. It's not that likely that I've run into it that I haven't been able to live my life without that special ADS feature and a feature and haven't implemented it.
Great. Here's a question. It's a little, I want to say it's a little off topic, but not really. Do you have any tutorials, meaning you, Mike, right, to help learn how to do some C code for the models?
Well, I do not have tutorials. What I have is examples.
What they say, or for examples, they're or just
well, the examples are, this is a concise example that shows how to do it. Now you'll also find there's a forum for QSpice, and there's some some source code shared, like for SPI. Somebody implemented SPI. You don't need to do I2C because I2C is actually a native circuit element in QSpice, because I've done so many models that communicate to other models in I2C. So receiving, transmitting as I2C is the native circuit element. Though actually I usually implement that in C code. If it's in a model, you should put it in C code, but I still need a test vector. So I have a native circuit element that would just talk I2C to some model I'm developing. Yeah, in the QSpice forum on Qorvo's website, you will find quite some discussion on C++ and some examples from people. But I don't have a video tutorial on that. There are a few tutorials. I get in that qspice.com page. I think you'll find up there. Oh, and these are also cited in the here's a few tutorials. These are rather dated. These are about a year old, so there's been a lot of advances since these were done. But you will find them there. And also you'll find in the help file, there's some tutorials. Not that I would ever be so condescending as to tell a person to read a help file. Okay, but you will find those links to those how-to videos. You'll find links to them there.
All right. Well,
getting back to machines, this is the machine I use. No, that's my old one. This is my new one. The radiator wouldn't fit inside, so it's just glued on top.
Mike, do you have anything else you'd like to leave the attendees with today? We're coming close to the top of the hour. I wanted to give you a chance to say anything that we might not have asked that you thought of along the way.
Oh, I don't know. I can give you all a big smile.
All right, we'll take it. We'll take it. This was jam-packed, so you
This
covered a
was.
lot.
All righty.
And the URL again? The URL again, Mike. What was the URL that you kept pointing to? Just to repeat it for everyone to make sure they got it. The one you just went to. It
Yes.
was
www.qspice.com. Now that's a vanity URL that directs you into Qorvo's website, or you can just type Qorvo.com and search for QSpice, which
awesome.
may be
Well,
easier.
yeah. Well, QSpice.com is pretty simple too. Well, thank you for joining us today for this live chat. Thank you to our sponsors, Mouser Electronics and Qorvo, and our amazing panelist, Mike. And listen, everyone, have a great day.
Thanks, Mike.
All right, thank you. I really appreciate your interest in QSpice because, QSpice is the only thing I do for a living. So if you think about it, in any final analysis, your interest in QSpice, for me, is a matter of life and death. Thank you.
Hi, thank you, Mike.
Thanks,
Have
Mike.
a great day,
All right.
everyone.
Bye.
Yep. Bye-bye.